G. We have the map IG from G to G given by IG of X is GX G inverse, right? You conjugate. So I'm sure you all understand this very well when G is like Sn, right? We know exactly what happens when you conjugate a cycle, right? But in general, we can conjugate by any for arbitrary group G. And I think it's problem 2, so we're just gonna go sort of linearly, right? An inner automorphism, show that it belongs to odd G. So in other words, we have to show IG. So in other words, we have to show it's an automorphism, right? So obviously it maps G to itself. So we just need to check it's a homomorphism, it's bijective and surjective, right? So surjective is quite simple, right? Because you literally just solve for the term, right? Like given G2, you solve for it, right? By like multiplying by G and G inverse on like both sides. So given Y in G, right? Want to show there exists X in G such that GX G inverse is Y, right? So, I mean, if you solve for it, multiply by G and G inverse on both sides, you'll get this, right? X is G inverse YG, right? So multiply by G inverse on the left and G on the right. So it's certainly surjective, right? There's an element that maps to Y. And it's injective by same argument, right? If IG of X equals IG of Y, want to show X equals Y. Well, this just means GX G inverse equals GY G inverse. So again, multiply by G inverse on the left, G inverse on the right. You get the result, right? And then finally, we need to show the homomorphism property, right? We need to show IG of XY is IG of X, IG of Y, right? This will show it's a homomorphism. So IG of XY is GXY G inverse, right? Now we need, a G and G inverse, but G and G inverse is just E, right? So between the X and Y, I can put in a G inverse G, right? I'm not changing anything because I just added in identity, right? But now this term is IG of X and this term's IG of Y, right? So IG is an odd G. Everyone clear so far? Okay. So, we denote ng to be the set of all inner automorphisms. So, and it turns out that this forms a subgroup of odd G. So, I'm not gonna prove. Associativity is a pain, so I'll skip that. So it's clear that we have an identity, right? The identity automorphism is you send every element to itself, right? But that's just IE, right? So remember, IE of like X is EX E inverse. But E inverse is E. So, and then EX is X. So this is just X, right? So we certainly have the identity. And hopefully it's clear that the inverse, right? Everything has an inverse, right? Because this composed IG inverse should be equal to IE, right? So I'm saying the inverse of IG is IG inverse. To see that, how do I show two maps are equal? Well, like this, the left-hand side is a map, the right-hand side is a map. So to show two maps are equal, you just have to show they map every element to the same thing, right? So IG compose IG inverse of X. So on one hand, this is, if you like, it's G inverse X G. So it's this, right? IG, right? So I'm computing this first, but G inverse inverse is G. So this is IG of G inverse XG. And now IG is, I remember IG is I do G and then whatever term I have and then G inverse, right? So it's G, whatever term I have, which is this term, and then G inverse. And it's clear I get X, right? So, and then obviously IE of X is X. And this holds for all X in G, so the two maps are equal, right? Everyone follow so far? So, okay. So from here, we still need to show that like it's closed, right? I'll leave associativity to you. It's really annoying and not that hard. But I mean, the point is like the group is associative, so it follows from associativity law of the group. But like we have to show this belongs to like in G, right? It's closed under the operation. In other words, what I mean is I need to show this thing is like I G prime for some G prime, right? So let's see that it is, right? So IH composed of like X is equal to IG of HX H inverse, which is equal to GHX H inverse G inverse, right? Now, this, if you recall, the inverse of GH is H inverse G inverse, right? Because GH times H inverse G inverse is GE G inverse, which is E. Yeah. So this is just the inverse of this. So another, we can rewrite this as GH inverse. So you can see that this is just IGH of X. So it's actually close, right? So when you compose two inner automorphisms, you get an inner automorphism. So yeah, hopefully that convinces you in G is a subgroup. Now we next thing is we want to show G mod the center is isomorphic to NG. Right, so in other words, that this is a subgroup of odd G, right? Let me put, so, so you see here, this is a common trick, but like, how do I say this? Like, if whenever you map from a quotient to another group, you have two ways, right? You either define the map explicitly, so you have like method 1, define map explicitly, but you see this, if you do it this way, it's very difficult. I mean, not difficult, it's a pain because you have to check well-definedness, right? Kind of like in your homework. Whenever you map, whenever your domain is a quotient group, you have to check an extra thing, right? That it's basically independent of like choice of representative. So you need to check choice of representative. So in other words, method 2, we have a better, we have the isomorphism theorems, right? It says first isomorphism theorem. It says if phi is a map from G to G prime, then G mod kernel phi is isomorphic to image of phi, right? So are you seeing what I'm getting here? So for method 2, this seems simpler, right? You just define map from G to odd G. Show kernel. What do we want the kernel? We want G mod kernel, right? Here we have G mod center, right? So show the kernel is the center, and show image is what we want, right? It's in G. This is ugly. Okay. Image is in G. Yeah. And then we're done, right? So in other words, let's define phi from G to odd G to be given by G goes to the map IG. Yeah, to be what we defined earlier. So it's clear that, I mean, it's clear image is in G, right? It's the group of inner automorphisms, right? Because everything is an inner automorphism. So the thing to check is, what's the kernel, right? And the kernel of phi is, what does kernel mean? It's the set of G and G such that phi of G, which is IG, is the identity, right? So in other words, right? But what does it mean? What's the identity? Identity in the automorphism group is just the map that takes everything to itself, right? So in other words, is the set of G and G such that, what does the map IG do to X, right? Given X for all X in G, IG of X is X, right? I mean, that's what it means to be the identity map. You map every element to itself, right? So, but we know what the map is. the map is given by GXG inverse is X, right? I mean, it's given by GXG inverse. Now, if I multiply by G on the right, I get GX is XG for all X in G. Hopefully you know exactly that means. It's, it means that G is in the center, right? This is exactly what it means to be in the center. You commute with every element in your group, right? So and then you're done, right? So by first isomorphism theorem, Gmod kernel phi is isomorphic to image of phi, but in this case the kernel is the center and the image is in G. Yeah. Everyone good? Okay. So let me just yeah, okay. So question, what is, let's sort of do examples of automorphism groups. So what is aught of Z? So this is maps phi from Z to Z such that phi is homomorphism, phi surjective, phi injective. So you have a map of cyclic groups, right? Like this is the map. So everything's determined by where one goes. So you obviously have one goes to one, in which case phi is identity map, right? Because I mean, if one goes to one, everything must go to, two must go to, like two is 1 plus 1. So phi of 2 has to be phi of 1 plus phi of 1, which is 1 plus 1. So phi of 2 has to be 2, so on and so forth, right? And that map is clearly injective and surjective. You can map to -1, right? So this will be like a non-identity map, and this certainly still remains injective and surjective, right? So like phi of 2 is phi of 1 plus 1, which is phi of 1. So this sort of like the negation map, yeah? -1 plus -1. So in other words, well, there should be a circle. So phi of, like, in this case, phi of m is like -m. Can you have anything else? If you send 1 to anything else, let me just write anything else. You it's a problem, right? You can't. It's not surjective, right? You're never gonna hit 1 in the image, right? Because if phi of 1 is like 2, you're never gonna get 1, right? Using the homomorphism property. And similarly, like phi of 0 is just the worst. If phi of 1 is 0, everything maps to 0. So basically, you see that for aught Z, it's only these two, and I'll leave it to you. But any group of order 2 is isomorphic to Z mod 2Z, but it's pretty easy to check. But yeah, so aught C is identity, and I'll call phi negate the negation map. Okay. So another example is aught of like, let's do like Z8. So again, the automorphisms of Z8 are maps what? I'm not going to do this completely, but phi from Z8 to Z8, right? Such that phi is injective and phi surjective, right? I certainly know 4 of them, right? I mean, everything's determined by where 1 goes, right? So I could send 1 to 1, right? That's identity. I could send 1 to 3, 1 to 7, 1 to 5. I don't know why I skipped 5. 1 to 5 and 1 to 7, right? So I have 4 maps. So I'll call this V1, V3, V5. I'll write class, yeah, the class. So I'll leave checking well-definedness to you. I don't think it's that hard. But can I get anything else, right? So I mean, you only have 4 other choices, right? You send 1 to 2, 1 to 4, 1 to 6, 1 to 0. And you could check that if you do that, it's not going to be surjective, right? Because like if you send 1 to 2, for example, after 4, right? 4 maps to 0, and then 5 maps back to 1, right? 4 maps to 0 because 2 plus 2 plus 2 plus 2 4 times is 8, which is 0, right? And if you do it again, you get back. Oh, sorry. 5 maps to 2. I don't know what I wrote. Why I wrote that, right? So if you like, phi of 5. I mean, to make it short, is phi of 4 plus 1, which is phi of 4 plus phi of 1. And this is 0, so it's just phi of 1, which is 2. So you see, it's not injective, right? Because 1 and 5 map to the same thing. And in fact, you could show it's not surjective either. The reason I chose these, this is clearly surjective and injective because 1, 3, 5, 7 are co-prime to 8, so they generate the whole group, right? So is everyone clear? Everyone good? Yeah, and then so you can see here everything's determined by where 1 goes, which and for it to be an isomorphism, it has to go to the co-prime things, right? So you see that aught Z8, you could show this explicitly, is isomorphic to U8. What is U8? Remember, this is exactly the numbers co-prime to 8, right? So hopefully you see why that's the case, right? Because we can only send it to numbers co-prime to 8. And this is like the numbers co-prime to 8 under multiplication, right? And hopefully you know the map, right? I mean, this thing contains 4 elements, right? Phi1, Phi3, Phi5, Phi7. So we send basically Phi A to A. So, I mean, just to convince you, right? I'm not going to do well-defined this, but like, if, you know, it's a homomorphism because if phi A, I mean, let's call it the map psi of phi A, phi B, we want to show that this is psi of phi A, psi of phi B, which is, we know what this is, right? So this is psi of phi A by definition is A, psi of phi B is B, right? So we need to show this thing is equal to this thing. Let me double underline, right? So, and you can see this, right? Because phi A, how do you compose 2 maps? So phi B maps 1 to what? 1 to B, right? So now we have to check where phi B, you know, phi A maps B. Well, phi A, right, maps 1 to A. So it maps 2 to 2A. So you see it maps B to BA. Yeah? So B to BA. So the composition, maps 1 to BA, or if you like, AB. Yeah? And so you see that phi A, phi B is just phi AB, the map that sends 1 to AB. So this is just psi of phi of AB, which is AB. Yeah. So you see that they are equal. Everyone clear? Clear. So hopefully that was not that hard. So you could show in general, general aught of Z mod. I mean, it's the same proof, right? But is isomorphic to UN. Yeah. Okay, so that's really all for today. So, but let me, go over more problems on first isomorphism theorem so everyone's comfortable. So let's define GL2 Z mod 3Z, right? These are invertible matrices with entries in Z mod 3Z. And I am gonna quotient out by. So remember, these are the things of determinant 1, right? So here, remember, GL2, just if it's invertible, it just means determinant's non-zero, right? So show this is, or show, not define, show this is isomorphic to U3, right? So again, let's practice first isomorphism theorem, right? So let's define a map phi from GL2 Z mod 3Z to U3. So let the plan, right? Define a map from here to here. And what do we want? We want kernel of phi to be SL2 Z mod 3Z, right? And we want image to be the whole thing, right? We want it to be surjective. So the image to be U3, right? I.e. it's surjective. Then we have our result, right? By first isomorphism theorem, like GL2 quotient kernel is isomorphic to image, right? Okay, so what should my map be? Any ideas? So it's actually not that bad. So like I need to send a matrix to a number. How can I get a number out of a matrix? What do you know? What operations can you do to a matrix to get a number? Oh, this is the question. It's just this. Right. So I need to map the group of matrices to like a number. I mean, class of a number, but in other words, but so how can I get like, I need a map, right? So like if I have a matrix A, how how do I get a number out of that? So you mentioned your some of you are taking math 121. So what operations can you do to a matrix to get a number out of it? So I mean it's not even 121. It's like I think math 3A. Should have probably learned it from math 3A. I mean, what operations, I mean, or what function can you apply to a matrix to get a number out of it? Like what have you learned in like linear algebra? Yeah, exactly. You also had another option called trace, but in this case it is determinant. So why is this? First off, let's think about it. Why U3, right? U3 is the invertible elements of uh, Z mod 3Z, right? In which case, since it's prime, it's just 1 and 2, right? The class of 1, class of 2. So you see why we need GL2, right? Because determinant of A, because we're in GL2, right? GL2 Z mod 3Z means invertible matrix, right? Which means determinant is not 0, i.e. determinant. So you see this is well defined. I mean, not well defined, but I guess you could call it well defined. Determinant of A is not 0, right? Because if determinant of A was 0, it wouldn't be in this group, right? So you need to make sure, you're actually mapping to elements in U3. In which case it is, right? You either map to, when you take operations, right? It's either equal to the class of 1 or the class of 2. Yeah. Everyone good so far? So do know you do need to check well-definedness, which I'm not going to do. I mean, well-definedness for like the thing inside, because we do have a quotient group here. But okay, let's move on. So is it surjective? We want it to be surjective. So i.e. this group only has 2 elements, right? 1 and 2. So i.e. give me matrix with to show it's surjective, I just need to find myself a matrix such that determinant of that matrix is, or A prime is 1, a class of 1, and determinant of A prime is the class of 2. This should not be hard, right? So I mean, class of 1, we could just take A to be like 1, 0, 0, 1. Yeah. So the right, and then I mean, only is that hard. So for A prime, you just take 2, 0, 0, 1. Yeah, there, done. It's surjective. Yeah, this has determinant 1. That has determinant. Did I do it right? Yeah, it has determinant 2. So it's surjective, right? So image is U3. Now, what's the kernel? I want to show kernel, right? So let's write out what kernel is. Did I denote the map phi, right? Phi, right? It's the set of matrices A in GL2 Z mod 3Z such that phi of A, which is just determinant of A, is equal to identity. But what's the identity in U3? It's elements under multiplication, right? It's the invertible elements under multiplication. So identity is 1, i.e., right? Determinant of A is 1. So these are matrices of determinant 1. By definition, this is SL2 Z mod 3Z, right? That's just by definition. So by first isomorphism theorem, I'll write it like this. Isomorphism theorem GL2Z mod 3Z. Is that what's the image, but since the it's surjective, the image is the whole space, so it's U of 3. Everyone good or comfortable with first isomorphism theorem? It's pretty useful whenever you want to show a map from like a quotient group to like something else. So let's do one more, yeah? So let's take, if you remember the unit circle, right? This is the set of z and the complex numbers such that absolute value of z, like basically it's the unit circle on the complex plane. So remember, this forms a group under multiplication, right? Oh, sorry, not z to the n. Absolute value of z is 1. Yeah, I don't know why I wrote n there. Okay. So the question is, show the group R quotient z, of course under addition, is isomorphic to T. So if you like, I'll write it like this. Right. But most problems in the book will just ask like this, because the operation is like implied. So again, we want to use first isomorphism theorem, right? So in other words, again, the plan is what? Define map from R to the unit circle, right? Phi, I call it phi, right? And then show phi surjective, and kernel of phi is the integers, right? So what is a map? The map you have to think of, but like, I mean, it uses stuff you should know already. So how do elements in the unit circle look like? Like how do you write an element in the unit circle? So this is I don't know what class this is. Yeah, so something like basically remember, if you go back to like the beginning, every element in unit circle is of the form e to the 2 pi I k, right? If you remember that, hopefully you remember that. Okay, that's the thing I'm assuming you should know. So okay, great. So obviously we have a k here. So let's map. Like it, I mean, it's the first thing you think of, and most of the time it turns out to be correct. So you map k to e to the 2 pi I k, right? So from this statement, right, the statement in blue underline, it's surjective, right? By definition, because every element is of that form. So yeah, so surjective is clear. So we just need to show the kernel is the integer, right? So kernel equals the set of k and r such that phi of k is the identity in this case, since the things in the unit circle is under multiplication. The identity is 1, right? So I need to show the set of phi k is 1. In other words, is the set of k and r such that e to the 2 pi I k is 1. So this should also just be knowledge of complex numbers, but ren is e to the 2 pi I k equal to 1. So remember, cosine of 2 pi k plus I sine of 2 pi k, right? So in other words, it's asking ren is sine and cosine, both, I guess. Ren is sine and cosine. 0, I guess. No, sorry, my mistake. So I want this to equal 1, right? So let me just, not both 0, but one of them is. So I want cosine of 2 pi k plus I sine of 2 pi k to equal 1. So 1 has no imaginary part, right? If you like, it's 1 plus 0 I. The imaginary part is sine of 2 pi k, so it better be 0, right? If I match imaginary parts. So I need sine of 2 pi k to be 0, and the non-imaginary part I need to be 1. 1. And you see that sine is 0 at, k pi, right? When k is an integer, right? And you see cosine is 1 at like 2k pi per k an integer, right? I mean, hopefully you all know this, right? It's 1 at like every 2 pi interval, right? So you see since you already have a 2 pi k, I mean, since you already have a 2 pi here, you see that k must be an integer, right? Does everyone agree? It's like trig, I guess. It's not even like college anymore. It's like high school trig. Yeah. So k must be in Z. Yeah. So by first isomorphism theorem, R mod kernel phi is isomorphic to image of phi, but it's surjective, right? So image of phi is just the whole unit circle. And then we showed that the kernel is the integers. Yeah. Is everyone comfortable with first isomorphism theorem now? hopefully you see its usefulness. Okay. So yeah, so like it skips, you see, that thing guarantees it's isomorphic, right? You don't need to like define a map from quotient groups and shows well defined, so on and so forth, right? First isomorphism theorem already just immediately gives you that. Okay, so let's just call it a day. Hopefully you enjoyed this course. So on Friday, I'll just have office hours for like last minute final questions. And then, yeah, good luck on your final next week. Do I know? No, the professor makes it. I don't make it.